Hello and welcome to the session. Mathematics for Computer Science LO1 Understand binary and the representation of numbers in different bases. How do computers understand information? It all starts with binary numbers. This video explores the core concepts of binary and other number bases critical to computer science. From binary representation to base conversions, some discover the mathematical foundations that power computing. Let's dive into the world of numbers that computers rely on. Number bases define how many symbols are used in a system. In base 10, humans use digits 0 through 9. Computers use base 2, known as binary, with digits 0 and 1. Octal and hexadecimal are shorthand for binary, using bases 8 and 16 respectively. Understanding these bases is essential for computer science. Binary is the base 2 system, where each digit is a bit. For example, the binary number 1011 converts to 11 in decimal. Each position in binary represents a power of 2. This positional value is key to understanding binary numbers. Binary forms the foundation of computer data representation. Converting decimal to binary involves repeated division by 2. Take 13 in decimal, divide by 2, and record remainders. Read these remainders bottom to top to get the binary result. This method is crucial for understanding how computers process numbers. Mastering this conversion is a fundamental skill in computing. Octal uses digits 0 through 7, grouping binary bits in threes. Hexadecimal uses 0 through 9 and letters A to F, grouping binary bits in fours. These systems simplify binary representation for humans. Hexadecimal is especially useful for memory addresses and debugging. Both are essential for efficient computing. Binary is favored because electronic circuits handle two states well. This simplifies hardware design and aligns with Boolean logic. All data, from numbers to images, is ultimately binary. This universality makes binary indispensable in computing. Understanding binary is non-negotiable for anyone in computer science. Binary representation uses only zeros and ones. Each bit represents a power of 2 based on its position. This method is used because hardware easily distinguishes two states. All computer data is encoded in binary form. It's how computers process everything from numbers to complex data. Changing bases means converting a number system without altering its value. Base 10, 2, and 16 are most used in computing. Each base follows positional representation rules. Conversions involve multiplying digits by their base's power. This fundamental skill is crucial for computer science students. Converting to base 10 helps understand numbers in other bases. In binary, each bit's power of 2 is summed for conversion. In hexadecimal, digits are multiplied by powers of 16. This method bridges different number systems to base 10. It's a key technique in computer science. Binary and hexadecimal allow direct conversion without base 10. Each hex digit represents 4 binary bits. Binary numbers can be grouped into sets of 4. This relationship makes hexadecimal a compact binary representation. It's widely used for large binary values in computing. Base 10 evolved from counting with fingers, suited for trade. Base 2 emerged with digital electronics, using on-off states. Base 16 was adopted for easier binary reading. Each base has historical and practical reasons for its use. Understanding these reasons enriches comprehension of computing systems. Binary uses only 0 and 1, fundamental in computers. Bits represent powers of 2, allowing large value ranges. This system is resilient to noise, crucial for reliability. Physical systems distinguish two states, enhancing robustness. Binary representation is efficient for storing and processing data. 2's complement represents negative integers in binary. The most significant bit acts as a sign bit. Inverting bits and adding one forms negative numbers. This simplifies arithmetic operations in computing. It allows consistent use of binary addition for all integers. Floating point represents real numbers like 3.75. It uses a mantissa and an exponent, similar to scientific notation. This allows representation of large and small numbers. However, it can lead to rounding errors in binary. Understanding this is vital for precision in computing. Binary is closely connected to Boolean logic. Each bit can represent a Boolean value, true or false. Logical operations like and, or, and not operate on bits. These operations relate to set operations in Boolean logic. This connection is crucial for low-level programming and hardware control. Correct. Binary is fundamental for scaling and reliability in computing. Its strengths align with how hardware functions. However, it is inefficient for human readability. Numerical precision is limited, leading to rounding errors. Despite drawbacks, binary remains essential for modern computing. Binary simplifies the design of hardware components. Logic gates, processors, and memory circuits align with binary logic. This efficiency allows for faster and more complex processors. Binary simplicity is key to stable and practical hardware. It underpins the evolution of modern computing technology. Binary provides a universal format for all data types. Numbers, text, and images are reduced to binary form. This consistency allows different systems to work together. It bridges machine code and high-level programming languages. Binary's universal nature is crucial for seamless computing integration. Binary is not easily readable by humans. This necessitates higher-level representations like decimal and hexadecimal. Abstraction layers introduce complexity and potential errors. Translating between representations requires careful handling. Despite challenges, abstraction is necessary for practical computing. Binary's floating point representation limits numerical precision. Many decimal values cannot be exactly represented. This leads to rounding errors in scientific and financial systems. Careful management is required to avoid unexpected results. Understanding these limitations is crucial for precision in computing. Theoretical alternatives like ternary or analog computing exist. These offer higher information density or different performance. However, building them reliably at scale is challenging. Binary's robustness and simplicity outweigh these theoretical advantages. It remains the foundation of modern computing systems. In conclusion, understanding binary and the representation of numbers in different bases is fundamental to computer science. Binary, along with other number systems such as decimal, hexadecimal, and octal, is used to represent data and instructions within computer systems. Understanding how numbers are converted and represented across different bases supports effective programming, data processing, and system design. This knowledge forms a core foundation for computing and digital technologies. Thank you for watching this video. If you have any questions, please feel free to contact us via email or WhatsApp at 074843616888.